Okay, let's look at the problems in our last slide, slide 24. We have Kb for the nitrite ion, NO2, minus, so the Kb is equal to 2.17 times 10 to the minus 11th. Write the formula and calculate the Ka for the conjugate acid. So let's first write the equation out, and then we'll write the Ka expression, and we can figure out what the value is for the Ka. Well, we know that this is a base. It's telling us it's a base. And NO2 minus in water, and remember this is liquid and this is aqueous, should give us, because this is acting as a base, it's given us the Kb. That means that it's going to strip off a proton, give us HNO2 aqueous, the conjugate acid of that base, plus the OH minus aqueous. This is a conjugate base of my acid. This is the reaction. So the Kb value is going to be, or the Kb expression is going to be HNO2, concentration of HNO2, multiplied by the concentration of OH, divided by the NO2 minus concentration. The Kb is going to be, or to calculate the Ka, first of all, it's asking us what is the formula for the conjugate acid. This is my base. This is the conjugate acid. They're related by that extra proton. This is the base. It's missing the proton. It strips it from the water. And this is the acid, the conjugate acid of my base. So this is my conjugate acid. To calculate the Ka, I know that Ka times Kb is equal to Kw. To calculate the Ka, therefore, I just divide both sides by Kb. Kb cancels out. I know the Kw. Once again, if it is not specifically told to you, you will assume that it is 1 times 10 to the minus 14 divided by the Kb value of 2.17 times 10 to the minus 11. This gives you a Ka value of 4.6 times 10 to the minus 4. 4.61 times 10 to the minus 4. This is the Ka value for the conjugate acid, for HNO2. Now let's compare the two. I have NO2 as a base that has this value, 2.17 times 10 to the minus 11. I have HNO2 that if it went in the opposite direction, it have this value, 4.61 times 10 to the minus 4, for an equilibrium constant expression, which is Ka value for the acid. Now, because the Ka value is larger, much larger than the Kb value, what that tells me is that HNO2 is a much stronger acid so it is a strong acid having a weaker conjugate base. And this is a weak base having a much stronger conjugate acid. Typically, they go hand in hand. So if you have a strong base, its conjugate acid is going to be weak. If you have a strong acid, its conjugate base is going to be weak. So the Ka values, you can compare Ka values between two acids, but you can also compare a Ka and a Kb value to tell you which is the base stronger. So is this going to be stronger than HNO2? Because HNO2 is stronger, what this tells me is that the reverse reaction is going to proceed more, meaning that HNO2 is going to dissociate into these ions more than NO2 is going to combine with water to give you that. So the reaction is going to lie mostly on the reactant side. This is true. So basically, this is a small value. This is a small value, which means that the top number is much smaller than the bottom number, which means that your reactants do not like to form products. And so this is because it's a weak base. Look at how small that number is. Because it's a weak base, it likes to stay as a base. instead of, it likes to stay this way instead of grabbing the proton from the water to give you HNO2. The opposite is true for HNO2. I mean, it's a stronger acid than NO2 minus is a base. Okay, let's look at the last problem. Determine the relative acid strengths of NH4 plus and HCN minus by comparing their ionization constants, meaning the acid dissociation constants, the equilibrium constants for the acid, so Ka values. Those are the same, similar terms. The acid ionization constant of HCN, so Ka for HCN, is equal to 4.9 times 10 to the minus 10. This is for HCN. The acid ionization constant of NH4 plus is not directly listed, but the ionization constant of its conjugate base, NH3, so Kb for NH3, is listed as 1.8 times 10 to the minus 5. To compare how strong the acids are, you need to know the Ka values of both acids. I don't have the Ka value for NH4 plus, but I have the Kb value for its conjugate base. So I can calculate, I can go up here and say Ka times Kb equals Kw. I can calculate Ka by dividing by the Kb, both sides. This is 1 times 10 to the minus 14 divided by the Kb, which is 1.8 times 10 to the minus 5. This gives me a value of 5.6 times 10 to the minus 10th for the Ka value, so Ka value of NH4 plus. This is my acid. This is the acid. This is the conjugate base of that acid. Now, I'm told to compare the Ka values between these two acids, so HCN and NH4 plus, and figure out which one is the strongest acid. Well, this is 4.9 times 10 to the minus 10. This is 5.6 times 10 to the minus 10. This part is the same, but this value is a little smaller than this value, which tells me because this has a slightly higher Ka value, this is a little bit stronger of an acid. Remember, the higher the Ka value, the stronger the acid. So between these two, this is a stronger acid. But when I compare the Ka and the Kb value, so now I'm comparing the conjugate acid to the base, I see that the Kb is a larger number, much larger number than the Ka, which tells me that NH3 is a stronger base than NH4 plus is an acid. So when I look at the dissociation of NH3 plus H2O, giving me NH4 plus OH minus, what this tells me, because NH3 is a stronger base, it's going to dissociate more, so the forward reaction is going to proceed more than the reverse reaction of NH4 plus giving me NH3 plus H2O, because the Ka of the acid, this acid, is a smaller value than the Kb of this base, which means that this is going to dissociate more into NH4 plus and OH minus. The reaction is going to lie towards your products instead of towards your reactants. Okay, this is the end of the chapter 14 problems from the slides. And you can ask me any questions. If anything is unclear, please work the worksheets, and you can ask questions on those as well and let me know. I will do my best to help you figure these out because they're difficult problems to deal with. So, okay, thank you.